I'm going to be talking about a joint paper with Lars Hansen. It's called Four Types of Ignorance. So Milton Friedman liked this quote from Josh Billings. The trouble with most folks isn't so much their ignorance as knowing so many things that aren't true. And that's a theme in lots of Friedman's work in macroeconomics. So our starting point is that in 1953, Milton Friedman advised against using quantitative macroeconomic models that were developed at that time to fine-tune an economy. He was very skeptical about it. And his argument was that ignorant about details of the economic structure made him recommend that the government do less rather than more in terms of fine-tuning. So what we're going to do is we're going to revisit and we're going to extend some calculations that Milton Friedman in 1953 made. I'll show you Friedman's case in a little generalization of his model, and then we're going to describe alternative ways that someone could be ignorant. And we're going to compare those alternative ways with the outcomes of Friedman's analysis. And I think you'll see why we're going to be talking about this in a conference in which Bayesian analysis is widely used. So I'll show you our version of Friedman's model. It's what we call a targeting model. So there's going to be a law of motion for this object X. And what xt is, it's an observed deviation from a target. There's some target variable, Friedman said. You can think what it is. Output minus quote unquote full employment output. Number of things could be. It's a scalar. It's observed at time t. It's fixed and known at time t. There's a control, that's a government decision variable, that can affect X next period. That's the idea. And the baseline, that model that Friedman started from, was a model where everything important was known. The W is an IID shock that's impinging on next period's target with a coefficient alpha. So in this baseline model that Friedman is going to deviate from, K, beta, and alpha are all known. So the objective was to minimize the discounted, the expected discounted sum of squares of the deviations from the target, so-called targeting problem. And under knowledge of the coefficients, the optimum decision rule is this. And a key thing to know is what the response of next period's target to your control is, this beta. And so in the early 50s, people were using, macroeconomists and econometricians were excited about using macroeconomic models to give advice to policy makers. And this is a simple example Friedman came up with as an example of what they might be doing. So that's the optimum decision rule. So what we're going to do is we're going to study how ignorance affects the decision rule. And there's going to be two kinds of ignorance we're going to talk about, extending what Friedman did. We're going to talk about ignorance about beta, this coefficient. And we're going to talk about ignorance about the conditional probability distribution of W, and which Friedman did not talk about. And notice that ignorance about the distribution of W, if I change the conditional distribution of W, say I make it depend on the history of the X's, and I make it non-linearly depend on it, it changes the dynamics of the model that we want to control drastically. Okay. So here's the four types of ignorance, and actually you'll be able to think of more types of ignorance. So the first type is Friedman's. There's a Bayesian decision maker. And what he knows is he knows a prior probability distribution over beta. He doesn't know beta, but he knows a prior probability distribution over beta. Our second kind is going to be what we're going to call a robust Bayesian decision maker. This is someone who has a prior, perhaps, but he doesn't trust it. And he wants to study the effects of alternative priors on his decision. And he's concerned about those effects. The third type of decision maker, there's going to be a so-called robust decision maker who doubts really this whole structure of the model. He doubts the conditional probability distribution of W, conditioned on the history. And then the final one, if I have time to get to it, is a decision maker who wants to express a desire to have decisions that are robust not just to this model, but to some models that are perhaps nearby, but have different parameter values, possibly time-varying parameters. The relationship between these two is intricate. Okay, so let's get started. We'll just review Friedman. It's a very famous analysis, which is widely cited in macroeconomics as saying, giving the case for doing less, the less you know about parameter values. So what Friedman's going to assume is our version of Friedman. He's going to assume that beta t is normal mu sigma squared, and it's IID over time. And this IID prior assumption, this goes back to De Finetti, asserts that information about beta t is useless for inferring beta t plus j. We're going to take the IID assumption seriously. So that's what the natural extension of what Friedman had in mind. Well, the outcome of this, the outcome of this specification of ignorance is the decision rule, rather than being what it was before, is this. U depends on today's state with this coefficient rather than this coefficient. And if you check it, remember our prior is mu sigma squared normal. That's what beta is. So what this says is the more uncertain you are about beta, the larger sigma squared, the less you do. It attenuates your response. So that's the nature of Friedman's argument. And it extends naturally to our little extension, a dynamic extension. Okay, so we're going to have a robust Bayesian. And first the discussion is going to be, our Bayesian buys into, this robust Bayesian buys into, I guess he's not a Bayesian, because he does not have a unique prior, and he doubts his prior. But what he's going to do is buy into this structure, except he's going to say he doesn't trust his IID prior. He does not trust that. And what he's going to do is actually construct a set of priors that are sort of nearby here, as measured by particular measure of discrepancy, entropy. He's going to describe that set of priors, and then he wants to know if he makes a decision, if he makes a decision, how does the decision rule perform across the whole set of priors? And he wants to construct a lower bound. Constructing bounds is a big part of Lars's philosophy. He's going to construct this lower bound, and not because he thinks the worst is going to happen, but he wants that lower bound is going to assure adequate performance across a whole range of priors. That's going to be the philosophy. So how are we going to implement that? We're going to use relative entropy to express the notion that priors are near the basic baseline Friedman prior. And what's relative entropy? It's an expected log likelihood ratio. So what we're going to do is we're going to, if phi was the original prior from Friedman's model, we're going to just multiply it by a log likelihood ratio and get a distorted density, F. So then we're going to form entropy. And what it is entropy is just the expected value of the log of the likelihood ratio evaluated with respect not to the original density, but with respect to the distorted density. So we're going to integrate with respect to the distorted density. So m's a likelihood ratio. So it's not a metric, but it's a measure. It's a non-negative quantity, and it's a measure of the discrepancy between two distributions. And our philosophy is we're going to put in a little bit of robustness. We're going to have a parameter that controls how close one density is to another. But if you kind of thought of this was a density, we're going to basically put an entropy ball, a whole set of densities. And we want to know how our decision rule behaves, not just at one density, but over the entire set of densities. And we're going to use a bound on that, get a bound on that. So Lars and I are going to use two operators that express preferences for robustness, prior robustness. One we're going to call an operator associated with what Lars and I call multiplier preferences, and the other is called another operator associated with constraint preferences. And these are all about, there's going to be a parameter theta, which is going to be a penalty parameter here. And here it's going to be, it's going to look like the same parameter, but it's going to be a Lagrange multiplier. And the key thing is the penalty parameter is going to be fixed, and the Lagrange multiplier is going to be a function of, actually it's going to be a function of the state and something called entropy. And here, entropy is actually going to, here, the difference here is, even though a theta here is going to be fixed, and entropy, call it entropy, is going to be a function of theta and x. So that's going to play a role later. Okay, so this T2 operator, why the T? Because it was a T1 operator. I'm going to tell you about that a little later. This operator is just going to be an indirect utility function. And what it's going to be is, we're going to impose the following problem. We're going to choose M, remember that's a likelihood ratio, to minimize the expected value of the criterion we want to maximize. So we're going to distort the density, and we're going to try to minimize it. But we're going to penalize whoever's choosing the minimizer by this entropy. So entropy is a non-negative number. The more distortion this minimizing agent imposes through this, the worse off he or she gets. So if you solve this minimum problem, take the minimizer and plug it into the objective function. That's expected utility plus theta times entropy at the worst case distortion. And that's an operator called T2. It's an operator. If theta is infinity, this is just the mathematical expectation. Okay. Actually, in the math literature, this is called a risk sensitivity operator. There's a couple nice books by Peter Whittle about this. Okay, so the worst case distribution, the worst case density is the likelihood ratio. It's given by this formula. Lars really likes this formula. It's exponential twisting. And if you stare at it, what it says is you increase probabilities at events you don't like, and you decrease them at events with good outcomes as measured by your utility function. So our worst case density is just going to be given by this worst case distortion times the original density. And this distortion, it's a statistical version Murphy's law. Events occur with probabilities inversely related to their desirability, and theta, this parameter theta, controls how much you exponentially twist. It's a really nice formula. You see things like this all over large deviations theory. Okay, so the T2 operator is, well, I just said how we're going to do it. We're going to form this calculation, which is actually, in many cases, really easy to do. Okay, so associated with a fixed theta is a worst case distortion and an entropy. So this is the entropy. And as I said earlier, this entropy varies with x and your decision, and of course theta. And that's going to play a role in something I'm going to show you in a minute. So this is one way that Peter Whittle, through the risk sensitivity operator, would approach a robustness analysis this way. And actually, I should mention a really nice paper by someone named David Jacobson that inspired Whittle. It's a 1973 paper in the IEEE transactions on automatic control. Okay, now this is actually related to some decision theory work that was done in the mid-2000 to 2010 by Klebanoff and others. They call it smooth ambiguity. And they talk about structures in which a decision maker refuses to reduce compound lotteries. And that's going on here in the background. Okay. Okay, so now a question you could ask is, why fix theta? Why not fix entropy? Well, that's what the C2 operator does. The C2 operator does, if it fixes entropy, and it solves this problem. Looks a lot like the other problem. It's a minimization problem. It's just minimizing expected utility. It's choosing a distortion to minimize, choosing a worst case distribution subject to the fact that, well, it's a likelihood ratio, a distortion, and the entropy is less than this number eta. So literally now, eta is the size of this entropy ball. Okay. And again, if you solve this problem, you're going to get exactly the same formula for the worst case distortion. There's going to be a theta, but now what theta is going to be, theta is now going to be a Lagrange multiplier on this restriction. Okay, so this is a common relationship between so-called penalty problems and Lagrangian problems. Okay, so so now all we're going to do is we're going to apply this to Friedman's model. There's a few details. All we have to do is to calculate. There's a Bellman equation. We're going to use, instead of expectations, we're going to use the T2 operator. Okay. So, and we're going to either use this T2 operator or the C2 operator. So I'll show you some pictures on what happens here. Okay. So again, so what have I done so far? So where am I? Okay. Remember, Friedman assumed that beta was normal, mu sigma squared. We're going to have an agent who doubts this, who has this prior, but if you ask him if he really trusts it, he says no. He says there might be some nearby priors. You ask him what he means by nearby, he starts talking about relative entropy. Relative entropy of what? A possibly distorted distribution of here. And this M is going to distort this distribution, this likelihood ratio. And M is anything you want it to be, so very different, possibly very different distributions, except it has to be within some entropy ball or satisfy that entropy penalty. That's the spirit. Okay, this is literally a prior sensitivity exercise. Okay, so here's what we got. Here's what you get. This is going to be the T2 operator with a fixed theta. I'll show you something else in a minute. Okay, so what's here is x on this axis, and here's u. And to begin with, this line right here is known beta. That's what Friedman was criticizing, known beta. And when x moves, you actually do a lot. There's a big slope. This line here is Friedman. That's unknown beta, but a trusted prior. That's a prior. It's a trusted prior. Okay? So this shows what Friedman wanted to show. The whole point of his example was you do less. And the less you know in terms about that coefficient, you back off. Okay, so what are these things? What are these things with wings? What they are is, these are the robust decision rules with fixed thetas. So one of them has a, what you do is theta equals plus infinity, that's Friedman. The penalty on the minimizing agent is so big, he just doesn't touch, he doesn't distort the prior at all. But as I lower theta, I increase robustness. And what happens is, for x is pretty small, you stay very close to Friedman's rule. That's what this says. But as x gets bigger, you do less and less. You become less and less active. Okay, so now when we turn on this particular representation of prior uncertainty, there's an interaction of, Friedman's argument that you do less, it becomes much more quantitatively important. So let's drill down and kind of see why. This graph is going to show you why. And here's what's going on. The top two panels, this is the worst case mean, and this is the worst case variance that's coming out of the minimization. And the worst case mean, it's actually going to depend on x. Depends on x. So what you'll notice is and what is beta? Beta tells you how powerful your instrument is. So what you notice is, as we deviate at x equals 0, you'll actually see the minimizing agent chooses not to distort at all. He just leaves the variance where it was, where we made it, and he leaves the mean unaffected. But for other x's, what he does is, in either direction, he lowers the effectiveness of the instrument. It becomes much less, and because he lowers the effectiveness, but he also increases the variance, so you don't know what's happening, and because of that, you end up doing a lot less. Okay, now here's a telltale what's going on. This is what's going on to entropy. At x equals 0, entropy, at the appropriate best response rule is just 0. There's no distortion. But as you increase x in either direction, entropy goes up in this fashion. It actually asymptotes. So that's telling you something, that for a fixed theta, the size of this entropy ball is depending both on x and your response. So for a fixed theta, the entropy ball is actually growing. So essentially the set of priors is growing. With that particular parameterization, that's explaining what's going on here. So you might say, and I think Lars and I would agree with this, and a lot of decision theorists, you actually want to freeze a set of priors. So you want to use not the T2 operator, but the C2 operator. So what happens there? I'll just skip this. What happens there is it changes things quite a bit. Because now what happens is I've just recomputed things, but now what's happened is I've frozen entropy. So theta now is a function of eta and x. It's a function of x and u. So now what happens is Okay, so if this line was the original Friedman rule, as I now increase the entropy ball, well, what you can show is this thing is very close to linear, and it's true that you do less, but you do less in this almost linear way. So Lars and I, like this little laboratory because it shows in a sharp way what the difference between freezing entropy and freezing theta is. So the T2 and the C2 operators are intimately connected because T2 is easy to compute, and you can use an iterative algorithm to repeatedly compute T2, get the implied eta, and then use that as an efficient way to compute C2. Okay, so here's what we said. Here's the Lagrange multiplier associated with the entropy constraint. So for a fixed eta, as you change x now, that Lagrange multiplier, eta is fixed. But as you change x, the amount of the Lagrange multiplier on the entropy constraint changes. So there's this, to Lars and me, it's an interesting relationship. So now I want to move on to another setting, another kind of ignorance. We're going to talk about ignorance about WT plus 1. All the stuff before assumed that you knew the distribution of WT plus 1, and you're playing on that heavily. Where were you playing on that? Well, I was computing expected utilities all over the place. So I was integrating over W. So now what we're going to say is there's going to be a baseline model, but the decision maker is going to take that baseline model now just as a benchmark, and he's going to surround it by other distributions. And these other distributions, again, we're going to use entropy. These other distributions are nearby, but they might actually have be conditional distributions. There are alternative conditional distributions of what? This. And there can be shifts in the function that include nonlinearities and history dependencies. This is so-called unstructured uncertainty. Because at the end of the day, we're just going to say this is unstructured uncertainty. I'm not, quote unquote, non-parametric, infinite dimensional. I'm not going to tell you anything other than there's another distribution and its relative entropy is moderate. Okay, so here's the T1 operator. I'm just going to look a lot like. What we're going to do is we're going to choose an M, but now what M is going to distort, what M is now going to distort, it's going to distort the distribution of the W. Before it was distorting the distribution of the betas. See, now I'm pretending I know beta, I know alpha, I know kappa, presuming that I'm backed off of Friedman. But now what I don't know is that conditional distribution of the W's. Now, if you kind of think about it hard, there's a way in which that includes not knowing kappa, beta, really, or alpha. Because I can just load up a lot into just changing the condition. I can load a lot of nonlinearities and dependencies, history dependencies, right into here. Okay, so if you solve this, again, we get exponential, you get exponential smoothing, exponential twisting, and you get a very simple formula for this operator. And the minimizing distortion, again, has this exponential twisting form. So we're going to apply that to this situation. And something's going to happen that surprised me. Okay. So now what the decision problem is, this actually goes all the way back to Wald. The decision maker is going to use a max-min. He's going to use max-min decision theory. He's going to be maximizing, assuming after nature minimizes. And actually, it's going to turn out under certain conditions that are delicate, called the Bellman-Isaacs condition, you can exchange orders of max and min. So there's going to be a two-player, the thing is there's a zero-sum two-player game where the decision maker is choosing U to maximize a criterion, while nature is choosing the distortion to minimize them. So given my decision rule, nature's going to do the worst. It's going to try to minimize it. And see, nature's actually helping me because it's showing me where my decision rules are fragile, the aspects of my distributional assumptions to which my decisions are fragile. So you work this out, and it turns out, you solve this, you work this out, and lo and behold, what happens is the optimum decision rule is this. And that rings a bell. That's the decision rule before Friedman. Being doubtful about the distribution in this particular context, not in many others. In this context of Friedman, being unsure about the distribution of W leads you to do exactly what you would do as if you were sure of the distribution, and as if you knew kappa and beta. So we don't confirm Friedman's intuition about doing less here. Now, kind of if you ask, so what's going on here? Well, if you drill down, proper thing to do is to drill down and analyze the zero-sum two-player game that's going on in this context. And actually, to talk about the off-equilibrium behavior of and what's going through the head of the minimizing agent, because it tells you, it leads somewhere. It's a logic that's going to lead to development in the mathematics and control theory literature called structured uncertainty. So it turns out like this. We're gonna pretend like we're the minimizing agent, and we're gonna think of remember what we're distorting. This was normal 0, 1 under the baseline model, Friedman's model. We're gonna think we're a minimizing agent, and we're gonna replace this. We're gonna replace this with I don't know. Let's keep it normal, but we're gonna actually. It's going to turn out we're going to want to keep it normal because of a quadratic objective. We're going to replace this with V and something else, and we're going to think about making we're going to make V depend on, well, the state and the control and a constant. So we're going to change everything. So that means we're going to pull a rug out from under the decision maker. We're going to pull a rug out from under him, and the decision maker. The decision maker thought that he thought that the decision rule was a particular. He thought it looked like this, but with not this here, not this here, and not this here. What we're going to do is we're going to the minimizing decision maker is going to screw up the coefficients. It's going to screw up the coefficients. Okay. So so he does that. So if here's the key observation. It's if that's what the minimizing agent does, then it's possible for the maximizing decision maker completely to offset any of those effects. And he can completely offset those just by adjusting his decision rule. So remember what we're playing, what the equilibrium concept here is a zero-sum two-player game. So the Nash equilibrium is both guys are doing the best, taking as given what the other guy is doing. So it's possible for the decision maker completely to offset this. So, but this choice, this distortion choice costs the minimizing agent this entropy cost. It gives him no benefit in terms of reducing the criterion of, so he won't do it. So what the minimizing agent will do, he won't distort the mean, he'll distort the variance. He'll increase the variance. So when we come back to here, the minimizing agent sets this to 0, and he blows up this variance. And this is the maximizing agent he can't, he's in a situation where the so-called certainty equivalence math prevails. So he can't do anything about that, won't do anything about it. And so the minimizing agent makes him feel worse, but doesn't affect his decision. So the punchline is, in this setting, Friedman's intuition is completely wrong. The original pretend that you know everything decision rule prevails even if you don't know the distribution, and you don't do less. Okay, so so this kind of situation has affected what people in the control theory literature do, because they actually want situations in which they want the decision maker to say, I want a rule that's robust not only to this minimizing choice in this particular structure, but I want it to be robust to this too. So what they do, and I'm going to conclude here, what they do is they do something called structured uncertainty. And what they do is they change the entropy penalty. Peterson and other people have done this in the late 90s. They change the entropy penalty to, what it amounts to doing is they draw an entropy ball, but they specify a particular model, and it has to be a particular class of parametric models, maybe with time-varying parameters, that have to be included in the set of statistical models over which you want robustness, meaning over which your value function or utility bound prevails. And that's our fourth kind of uncertainty. And we have an example of how that's done. I'm not going to talk about that just because I'm out of time. It's actually, following Peterson, it turns out to be quite easy to do. So we've done that. And when you do it, well, guess what? When you do that in a natural way, you get a version of Friedman's rule, except that what was an increase in sigma squared is another object. And it's an object that has to do with your particular class of parametric alternatives to the model. Okay, so for us, this is a natural laboratory. Friedman's model is a natural laboratory to. I'm just going to flip to my conclusions. It's a natural laboratory to talk about robustness and its effect in prior uncertainty and model uncertainty in situations in which you either you can't or refuse to be a Bayesian on macroeconomic decision making. But Lars and I think this was a worthwhile starting point, partly because the Friedman example is so widely cited and it's so stripped. So many things are stripped down. But let me issue some caveats about this example. First, the model is not a modern macroeconomic model. First, it's a single agent problem, but it's even not really it's not really perhaps the most interesting single agent problem. And there are other problems that if we set it up this way, using very similar things, the argument about doing less, Friedman's hunch about doing less has been entirely reversed. And there's another logic that happens in some of these models. And these are simple macroeconomic control models in which the logic of, well, you're kind of uncertain a lot about the dynamics. So what you do is you do a lot now, even though you don't completely understand the structure, and then you pick up the pieces later. And there's examples where that prevails. So what caution means, it may mean doing more or maybe doing less. A lot depends on the details. So another thing is multiple agent settings. Okay, so in multiple agent settings, you notice in this setting, there's a kind of a civil war within the soul of the decision maker, because he divides himself into a maximizing and a probability choosing minimizing agent in order to study robustness. Well, in multiple agent models, there's multiple agents doing this, perhaps, and they have to have a view about what other agents are doing. So that the common knowledge or rational expectations assumption that prevails throughout modern macroeconomics and microeconomics has to be adapted to comprehend situations in which agents doubt models. One way to think of the common knowledge of the rational expectations model is it's a communism of models where everybody has a common prior. You have different information, but common prior. And then you'll notice I left ignorance of K out. That could be really important because K was governing the dynamics. So there's all sorts of interesting work, some involving Keston processes for describing complicated dynamics of such things. So these are just some of the things that Lars and I have been thinking about, and I appreciate your patience in listening to me. And I regret that I couldn't be at this conference for some personal reasons. But thank you.